So, welcome to strong field laser physics. Let me briefly remind ourselves what we did last time, and actually even the time before. So, we were considering the case where the electron is born at some time t0, right? Then accelerated by the field and then driven back to the field where it does something. And at what we looked last time in particular was that it scatters elastically. And we'll continue on that today. Last time we were considering the case where the electron rescattered. So meaning that it's scattered back. It's scattered by 180 degrees. So we said that it changes its velocity from y to minus y. Today we want to generalize this and actually consider the case where the electron scatters by some angle. And this is actually something beautiful, well, as the things before. So let me start with the headline. It's called laser-induced electron diffraction. So let me give you a brief preview of what we are going to do. So we have this electron returning to the core or to the parent atom, or actually it might also be a molecule, by the way. Yeah? And this is of course an important case as it will turn out. So we have an electron that collides with a target, and this is of course a scenario that is not new at all. Rather, people did this for a long time, that they did scattering experiments of electrons, using ions, using whatsoever. But here the special thing is that we have a precise timing of the electron that returns, and actually that we have a huge current. So if you use a regular electron accelerator and shoot on some gas, then of course most electrons will miss the atoms because they are so small, right? But here we always hit. Yeah? So this is something very special. So the current density that we have is very high, and in addition, something that you could never, I wouldn't know how to do it otherwise. That you could hardly achieve by any other means is that you have a well-synchronized electron. Yeah? So we know when it was born relative to dynamics that's going on in the atom or in the molecule. Yeah? So a very specific and very intriguing scenario that we have. Okay, so let's take just a few notes just to introduce this thing here. To quickly take a few notes of what I've just explained. So far, we had backscattering. Which means a scattering angle of theta equal to 180 degrees. Yeah? And of course, we got a maximum for the electron drift energy, which was 10 UP, and all these things. Yeah? So what we want to do now is an arbitrary scattering angle. So you know what we have is, say this iron core, and we pull out an electron, we accelerate it, yeah, back to and it hits back here, and and then it scatters at some angle, say scatters in this direction, and then the scattering angle would be this one here, right? Once again, we have this momentum here, this electron momentum, yeah, that so of the returning electron, and then we have this electron momentum after scattering. Okay, actually we have everything that we need. Yeah, so we can go right away about the mass and write down a few equations. So so the velocities in x and y direction. Now we have not only the x component but also the y components. So the electron velocities x dot and y dot immediately after scattering. Yeah, so after scattering, so meaning at t equals t1 plus epsilon. Yeah? So there we would have m, or actually these are the momenta, but never mind. So that's t1 plus epsilon. This equals mv of t1 times the cosine of theta, right? And the same thing, or the analogous thing, with the y component. There we have the sinus. Yeah? And then we do the same thing as we did before. We use conservation of canonical momentum. Yeah? So we just need to add the canonical momentum at this time t1. Yeah? So the drift velocity after scattering follows from conservation of canonical momentum. So this means we need to add A of T1, yeah? Or rather Q times, so charge times A of T1. But we are using atomic units. Yeah? So this means that the drift velocity is given by the canonical momentum. So we have minus E of A, let's write also E here, of T naught plus E A of T1, and now times the cosine of theta plus E of A T1, right? And for the other one, we have minus E of A T naught plus E of A T1, and here the sinus of theta. Of course, we don't add the vector potential to the y component, because the vector potential of the laser has, of course, only a component in x direction if we assume that it's linearly polarized. Yeah? So therefore, this A of T1, of course, only in the x component here. Yeah, and you see immediately what we have, right? So this is, so if you look at this, so we have it here in the x and in the y component. It's the same thing, so it's the radius. It's a radius, and here, so what we have here is the parametric representation of a circle. So this here is a circle. Well, it is offset. It's not a circle. Well, if it would be only this thing here, it would be just a circle around the origin. But it's offset here by this amount. So the above equation is the representation of a circle around the coordinate EA of T1 and 0, right? Its radius is this thing in square brackets. So we have minus EA T0 plus E of A T1. Yeah? Well, this calls, of course, for a figure, and here it is. Here it is. Let's see whether it comes. Yes, here it is. Yeah. So you see, there are actually two circles, because we have an oscillating field, so it can collision can happen from this side or it can happen from this side. So I've drawn this a little bit in faint colors, so let's only look at this one here. And you see, this here is the origin, and well, we have a circle of this radius, so just the one that I indicated above, right? And it is displaced from the origin by this amount here. Okay, well, sounds like theory. Let's see what the experiment says. So let's see what the experiment says. Here it is. So this is something that we did together with Lou Koch's group. So I introduced Lou Koch when I introduced the reaction microscope. So he's one of the co-inventors of that. And my pointer again doesn't work. What a shame. So, yeah, here it is. Yeah. Okay. So you see the same thing here. It is depicted here for a certain tubule of T0 and T1, right? Which is about the maximum. So it's not entirely correct in this publication. But you see here on a two-dimensional figure, I don't even remember what we ionized at that time. Well, this is actually just water vapor and hydrocarbons. So just the background gas. So it's just shooting at the background gas and looking at the photoelectrons. And you see nicely how this is actually followed. Well, you see a lot of additional questions would arise, of course, if you look at this thing, and we'll come to that later. Here another figure where actually xenon was used at different laser intensities, and again you see these scattering rings nicely, particularly nice perhaps here and here for higher field strengths. For higher field strengths, meaning or implying that the energy of the photoelectron, of this recolliding electron, is higher. So you can imagine that this is perhaps a more favorable condition for using these electrons as a probe. Yeah, so for using these electrons to probe the target ion. Yeah, so quite an intriguing concept that we probe the electron with itself. It's kind of a selfie that we are doing, right? And so we scatter these electrons which came out from the xenon itself. Yeah, we probe the xenon atom in this case. With kind of something drawn from the xenon atom itself. Yeah, and you see these circles here nicely. There's structure on these circles, right, which is intriguing. Okay, well, one remark on that. Yeah, so the thing how we treat that, and actually this was already true for what we did last time when we looked at exact backscattering. So what we are doing here, or the mass and analysis that we are doing here, is exactly the same as for the attosecond streak camera. Yeah, for the attosecond streak camera, we use an XUV pulse in order to put an electron into the continuum with a certain initial momentum. Right? So here, this role of the XUV pulse is played by the electron rescattering, yeah, in all directions, for example, and then we add this the canonical the vector potential at time t1. Yeah, so let us write down this remark. Yeah, so the above analysis is the same as for the attosecond streak camera. The attosecond streak camera. Yeah, so there an XUV pulse, is used to create a photoelectron, to create an electron with some initial momentum that subsequently is streaked, yeah, deflected by A of, well, if the pulse, the XUV pulse arrives at T1, then it would also be streaked by A of T1, right? There, an XUV pulse, say, arriving at T equal T1 is used to create an electron with some initial momentum, and to that momentum we would have to add A of T1. Yeah? Okay, so next point. You have already seen that there is structure in these, well, in these scattered electrons, and in the same way as you would do for a conventional scattering experiment, it is natural to introduce the differential scattering cross-section in order to describe the physics. Yeah? So the angle and energy dependence of scattering is described by the differential cross-section, by the differential cross-section. I will introduce an abbreviation for that here, so DCS. And this DCS, this differential cross-section, is given, is denoted sigma, right? Depends on angle and the energy. Yeah, so it's described by the differential cross-section of the atom, or it can also be a molecule, of the atom under investigation. Yeah, and d omega is, of course, the differential solid angle. Yeah, so this is sinus theta times t theta d phi. Yeah, let's look at the simplest possible case, namely at the, let's look at hydrogen, yeah, or rather the proton, so the hydrogen core nucleus. So the simplest case, this would be scattering of H plus, yeah? And the cross-section is, of course, known since a very long time, namely since Rutherford's time. Yeah? So that is Rutherford scattering. Yeah? And yeah, so if B is the impact parameter, as usually discussed in terms of the impact parameter. So how far, if the impact parameter is 0, then you hit it head on, and otherwise, well, it's only, you don't hit it exactly. So then we would have that theta is equal to 2 times the Arcus tangens, the inverse tangens, minus z, which for hydrogen would be 1. And then we have 2 times the kinetic energy times the impact parameter. And then we can write the differential cross-section. Of hydrogen, so it equals minus z times 4 times the kinetic energy times 1 over, and this is interesting, the sinus of theta half. Yeah? So what this means is that for hydrogen, there is not much for backscattering. Yeah, so for backscattering, which backscattering is theta equal to 180 degrees, because we have then because then the sinus to the fourth power of 90 degrees is equal to 1. Yeah? So in contrast, forward scattering is of course, this is a completely different story. Yeah? So in contrast, forward scattering so there, so then 1 over this expression here diverges. So do we see that? Well, we do. Let me show the data. So these are ATI spectra that I measured together with Phil Colosimo in Lou DiMauro's lab, because Phil Colosimo at that time had built a unique laser. At least at that time it was unique. It was a mid-infrared, mid-infrared. It was an infrared laser, lasing at 3.6 micrometers. And actually our plan was to do something different, so we wanted to look at alkali atoms. But just for a test, we did an experiment with xenon, and this was the result. Right? So, so you see that, so these are spectra actually taken for different intensities. Now, so the intensity is only changed by a little bit, but what you see here is that at these very low energies, there is this enormous yield of photoelectrons. Yeah, so here the same thing on a logarithmic plot. And you see, on a logarithmic plot, it doesn't look very prominent, but if you know that it's logarithmic, it's of course clear that this is an enormous effect. Yeah, so later they did it in Lou's lab with a lot of systematically. So you see the same thing, some comparisons to previous theory, right? And it didn't fit at all so this was the status when this paper was submitted. So it didn't fit to earlier theory. Yeah, so it could not really be reproduced. But it is a very general effect. Yeah, so this was not actually for hydrogen, but of course this forward scattering enhancement exists for basically all atoms. And so here you see a graph so where this was done at different wavelengths. And you see how prominent this becomes if one goes really to the regime where this kind of classical arguments where it really holds. And particularly interesting one is this one here. Right, so this was done at different wavelengths, but also different intensities, and the intensities were chosen such that the ponderomotive potential is the same in all three cases. Yeah? And you see these curves, they fit very well. Another classic experiment that one would do in such a case is, of course, to use linear polarization and circular polarization. And you see again, the effect is gone if you use circular polarization, which is a strong hint that it has to do with recolliding photoelectrons. Okay, so this is one manifestation of this simple thing here. You have a question? Yes, yeah, so what we said so far. Or how do we see it in this class? Okay, yeah. Yeah. So the question basically is, how do we see that this is forward scattering? Right, so first of all, what is forward scattering? Yeah, so as I said, last time we looked at backscattering, right, going this way. And forward scattering would be that it just goes through, right? Of course, you are kind of right that the word scattering sounds a little bit awkward in this case, right? So you agree if it is scattered by 1 degree, then you would speak of scattering. If it is scattered by 0 degree, well, we still should talk about scattering because you see it actually does something. Yeah, so this process of the electron going over the target atom does something to the electron. So it's scattered, forward scattered. The second question was, how do we see that that these things here are actually a manifestation of forward scattering, right? So this was the other question. Well, it was not, so at the time when this discovery was made, it was not, it was not so, it was not obvious. It only later became obvious. That it has to do with the returning electron is clear. That it's not backscattering is also clear because there's a lot of energy in that, right? Also, this analysis with the Rutherford formula is a good indication for that. And actually, I have another one. Actually, I didn't want to show it, but perhaps because of your question, I would show it. So this graph here. Yeah? So what I did here is the following. I have drawn these, so what I've shown so far, maybe I should draw it bigger. Yeah? Let me remove it again and just draw it bigger on the next page. Yeah, so what we have discussed so far was basically this circle that gives the highest electron energies for backscattering, right? But now I could also look for all the other tubules of T0 and T1, right? And for any given T0, there are, for any given energy, photoelectron energy, there are two tubules that do the thing. Yeah, so the short trajectory and the long trajectory. So so I have drawn these circles also for 9UP, for the short trajectory and for the long trajectory, right? And you see these circles. And what you see here is this, so at low energies, this is really, you really have a lot of trajectories that kind of accumulate there. This is not the full story because this doesn't include, so the Rutherford scattering. So there's no Coulomb interaction here involved. Yeah, but this, of course, includes the Coulomb forces. Yeah, so you have this electron that returns, scatters forward, and so there is, so the trajectory is, of course, influenced by the electrostatic field of the nucleus, right? And all of that is included in this formula. Plus, you see it from here, there are actually a lot of trajectories for forward scattering that have a very low energy. Okay, well, this is an idea, and the next thing was actually to make a theory out of that idea, right? And the idea, so the respective idea is quite straightforward. What you say is, well, I have this electron that returns with a certain velocity, and so I just use the cross-sections that my colleagues have found in the past decades when they did these experiments with electron accelerators, these conventional electron diffraction experiments. Yeah, so these cross-sections, they are known. And so we just use these cross-sections in order to make a theory out of that. So next point here would be the theoretical modeling. Yeah, the idea is expand the classical model, or if you use a semi-classical one, yeah, the classical or semi-classical analysis by differential cross-sections known from conventional electron diffraction experiments. Experiments, or of course also calculations, theoretical calculations. Yeah, and okay, yeah. So, and this has been done by the group of Shidong Lin at Kansas State University. Yeah, so he calls that quantitative rescattering theory. Yeah, so rescattering theory. Yeah, and actually these experiments are in good agreement with what is measured. So let me show here one recent measurement that we did in Hungary at the ELI facility, where they also have a mid-infrared laser system. And here you see two cases, namely the one of xenon and the one of krypton, right? And it's just amazing how, well, you see, if you know for what to look, you see these two scattering circles here, right? So you see these scattering circles, definitely. Yeah, you also see them here. But the structure is, there's a huge difference in the structure, right? So for krypton, yeah, so it seems that the scattering cross-section for backscattering is more or less, well, it's not zero, but it's quite low, and it's just the opposite here for xenon, right? So one of the things that we plan to do is to look at that. So doing this at mid-infrared wavelengths regions is of course interesting, because look at these momenta. Yeah, so it's 8 atomic units, which means if you calculate the kinetic energy, then you have 1/2 mass times, you have 1/2 times momentum squared divided by mass. Yeah, so in atomic units, mass is equal to 1. So what we have to do is just to calculate the square of 8, which is 64, divided by 2, which is 32. And then we have to calculate how much electron volts these are. Yeah, so we multiply 32 with 27, which is approximately 1,000. Yeah? So we have a kilovolt electrons here with which we probe. Yeah, so really remarkable. Okay, let's go one step further. Actually, the point with the kilovolt brings me actually to the next point. Yeah, so there's a question. So the question is, why do we use only noble gases? Yeah. So we will in a minute we'll come to molecules actually. Yeah. Why are people using noble gases for many of these experiments? Why are they using or if it comes to molecules, then a preferred molecule is actually oxygen or nitrogen or something like that. Well, these are convenient. First of all, they are convenient to work with. They are not poisonous, they are gaseous, so you can easily experiment with them. More importantly, they have a high ionization threshold. Yeah, so if you use 800 nanometer laser, and if you would use alkali atoms, then it would be hardly possible to apply strong fields to get a Keldysh parameter that is in the range of 1, right, and not 10 or so. Yeah? So in order to get to the tunneling regime, you need at least, if you don't have an infrared laser, yeah, so for infrared laser, you can also go to the tunneling regime with alkali atoms or atoms with lower ionization threshold. Yeah, so these are the reasons why noble gases are a preferred target, at least for the pioneering experiments. Yeah? And of course, this course deals predominantly with the with the pioneering experiments that have been done in the field. But of course, as the field evolves, people look at more and more complex systems. Yeah? And we come to them, right now. So having recolliding electrons with a high energy is actually necessary in order to do reasonable diffraction experiments, because we want to have de Broglie wavelengths that can probe not just the valence structure, but can probe the structure, say, of a molecule. And there you have to scatter at the inner shells, yeah? So, or even at the nucleus, yeah? But not at the valence shell. Yeah? Okay. Yeah? So the goal of modern electron diffraction experiments is to probe the molecular structure potentially with ultra-fast time resolution, as enabled by these recolliding electrons with ultra-fast resolution. Yeah, what follows is we need a high electron momentum such that the de Broglie wavelengths is shorter than the internuclear separation. Yeah, and there we can just look at the numbers. Yeah, so say we want, so the de Broglie wavelengths, I call it lambda e. Say we want that lambda e is smaller than the internuclear separation that we estimate with 2 atomic units, so which is basically 1 angstrom or so. Yeah. Yeah. Then we can just calculate P is equal to h over this de Broglie wavelengths. Yeah, so if we do this in atomic units, then we have 2 pi over lambda e should be larger than pi times the atomic unit. Yeah, and then we would calculate the energy, kinetic energy of the electrons. So we get pi squared divided by 2 atomic units, which corresponds to something like 134 electron volts. Yeah, so we would need at least this electron energy. And now we can ask ourselves, what kind of laser do we need? Yeah? So what kind of laser can provide this? Yeah? So just to be clear, so these 134 electron volts, this must be the kinetic energy of the electron that returns, right? So this corresponds to the 3.17 UP, not to the 10 UP. Yeah, the 10 UP, they are only achieved afterwards, after scattering. But we need this at the time of scattering. Yeah? So let's write is needed at the time of scattering. Can provide this. Yeah, so 3 UP should be, or 3.17 UP should equal 134 electron volts. Yeah? Well, if you do this at 800 nanometers, you would need 7 times 10 to the 14 watts per square centimeter. Yeah, so you see, this is a problem because ionization saturates even for a rare gas atom like argon already at, well, half of that intensity or so, right? So you can't really do this with an 800 nanometer laser. So actually, when I discovered the ATI plateau in 1993, 1994, one of my first thoughts was to do this experiment, right? To do such an diffraction experiment. But of course, I had no chance, and did not realize this at that time, because these things were not clear enough to me at that time. I had a laser with 630 nanometers, not even 800 nanometers. Yeah, so you see, one needs to go to longer wavelengths in order to have a chance here, right? So 1.1, so for 2000 nanometers, 1.1 times 10 to the 14 watts per square centimeter would be would be sufficient. Yeah? So let me make this remark. Yeah? This is beyond the saturation intensity. So now you might ask, why don't we use even longer wavelengths? Well, we did here, but there's also a penalty. There's actually a huge penalty to pay if you go to longer wavelengths. Now the point is, and this is something that we didn't consider so far, the point is that an electron wave packet driven by a long wavelength laser has a travel time that's larger, of course, right? It goes proportional, so it is proportional to the optical period. Yeah? And the wave packet, the electron wave packet, is a quantum mechanical thing, so it disperses. Right? So this means that this wave packet gets bigger and bigger and bigger, and when it returns, well, the current is still high, but it's much lower than for shorter wavelengths. Yeah? So this is a huge penalty to pay for that, because the scaling is actually very unfavorable. It goes with lambda to the 5th power or so. Yeah? And to one has to discuss this in detail in order to understand that. Good. Yeah. So, and these experiments, they have been done with molecules. So the first paper, again, by the De Mauro group. So you also see Zedong Lin with his quantitative rescattering theory here. But again, you see this, these nice scattering rings here, right? And now they looked, they took the data around the scattering ring, yeah, and plotted that here, right? So the squares are what they had from this experiment. The green circles, as far as I remember, they are from conventional experiments. Yeah, so there should be a literature reference on that in the paper. I didn't check it yesterday. And the red curve is, I think, a theory curve, right? And in that paper, this was done for different molecules. Yeah, so for nitrogen and oxygen, for different. Yeah, so this experiment. Yeah, so so this kind of experiment was done for nitrogen and for oxygen at actually 3 different wavelengths, according to the paper. And what they calculated is what's called the molecular contrast factor. Yeah, so there, I don't want to go into details here, but there the idea is to well, if you have a molecule like nitrogen, then of course you have 2 nitrogen atoms. Yeah, so you can consider the molecule consisting of 2 nitrogen atoms. Each of them has a scattering cross-section, the atomic scattering cross-section. And what you would try for a molecule is to take this atomic scattering factor out of the quantity that you measure. So you kind of normalize it to the atomic scattering factor. And this is this molecular contrast factor. So, and they measured that and determined the bond lengths, yeah, and, pioneering paper. The final paper that I want to just mention here by Jens Biegert's group and many people that are well known in the field. Stefanie Gräfe here from Jena. Yeah, so the inventors of the reaction microscope. Joachim Ulrich, Robert Moshammer, and many others. And they looked at a chemical reaction, right? So they took a snapshot. I think they call it a selfie of this molecule, C2H2. So a few femtoseconds after the reaction occurred, right? So this kind of things is possible with this technology. It's not; these are not easy experiments. One has to say, right? So they are really demanding experiments, and of course, the goal of the field should be to make these experiments standard methods in the for this kind of research, right? So this is ultra-fast chemistry. Yeah. So with this, I would like to conclude this first lecture, and in a few seconds we start with the second lecture. Thank you.